So, after discussing the me part, the substances that stay together when we drop them into a bucket of water, now I want to look at the dia part. Now, some of these will stay together as well. However, there are situations where each of these will dissociate or ionize into different ions. So, let's break these up. First, we're going to start with acids. In acids, if you flip to your acid table in your data booklet, so that's the table on page 8 and 9. Okay, it's a big long table. You will see that there's a gray line up at the top. The six acids above the hydronium ion, above that gray line, those are strong acids. And strong acids will dissociate into ions. Weak acids will not dissociate into ions, they're going to stay together. Now, both will conduct electricity because even a weak acid will dissociate a little bit. However, in this exercise, when we're writing down major entities, we're writing down majority of what you would see. So if I again was to look at this, I would find my table, I would look up hydrofluoric acid. Again, it's called an acid, so I know this is an acid. However, this is a weak acid. So when I'm looking at this and I look it up, it would be HF aqueous. And since it's a weak acid, we know it's below the line, therefore it's not going to dissociate. So when I drop this into water, it's going to stay as HF aqueous, and of course, water is present. Hydroiodic acid, however, is different. Again, we know it's an acid. So when we check our acid chart, we will see this time it's a strong acid. And so again, I'm going to copy the formula for hydroiodic acid is HI aqueous because it is above the hydronium ion or above the gray line. It's one of our six strong acids. When I drop it into water, it is going to completely ionize. So it's going to break into hydrogen ions, iodine ions, and of course, we have water. So the difference here is in Bia, there is a possibility of something breaking into ions. For acids, strong acids ionize, they break into ions. Now, for bases and ionic, we look at these together. For acids, we check the acid chart. For bases and ionic, we are going to check the solubility chart located on page 6 of your data booklet. So this is how it works. If something has high solubility, it wants to dissociate into ions. So if it's highly soluble, it'll break into ions. If it's got low solubility, it wants to stay together. And you know this already because when it has low solubility, you always write it as a solid. It wants to stay. So lithium fluoride, positively charged, negatively charged, metal, non-metal. We know this is ionic. If I think about writing this, lithium is one positive, fluorine is one negative, so this is going to be LiF. And if I check my solubility table, this has low solubility. Well, the moment I know that this substance is LiF solid, it's got low solubility, I know that when I drop it into water, it's going to stay together. And of course, water is going to be present in the example. Let's try another one. Sodium sulfate. Again, it's an ionic compound because it's made up of a metal and a non-metal. Sodiums are metal. When I check the solubility table, I would write it down as Na2SO4. This guy is, of course, group 1, highly soluble. So when I drop it into the bucket of water, the moment sodium sulfate hits, it's going to be Na positive, going to break into its ions. SO4 2 minus, ions again. And of course, water is present. We are not making a list of how many of each. So I agree for every sodium sulfate that dissociates, I would have 2 sodiums. We're just making a list of what would you see, not how many. The last one we're going to do is strontium hydroxide. Because it's a hydroxide, we know for a fact this is a base. So when I go to write this, this is strontium SR bracket OH bracket 2. I checked my solubility. This has low solubility. So when I drop it into water, because this is low solubility, it's going to stay together. And of course, also water is going to be present. That's the one thing I like. Water is present in everything. You always have to write it down. Okay. So in Baya, strong acids break into ions. Bases and ionic, if they're highly soluble, they break into ions. Everything else stays together. So what I would like us to do is, can you please pause the video, copy all 8 of these, and I would like you to try them for yourself, then check your work. In each example, I want you to do it the same way that I did it. Determine, is it a base, ionic, acid, molecular, or an element? Secondly, how would I write this compound before I drop it into water? And then thirdly, what am I going to find for the entities once I throw it into a bucket of water? Please pause the video now. Well, if I look at these, glucose is a memorized molecular compound. Glucose is one that we have memorized already, or I guess you could look it up. This is C6H12O6. We know glucose is a solid. Now, the question is, because it's memorized, is this on my Shag-Me list? And the answer is yes, it is. So when I drop it into water, it is going to stay together. However, the state is going to go to aqueous. And of course, water is present. Calcium fluoride, metal, non-metal. So this is going to be ionic. When I think of calcium fluoride, I have CaF2. I'm going to check my list. Calcium fluoride is low solubility, so we're going to write it as a solid, which means when I drop this into a bucket of water, it's going to stay together as a solid. And of course, we have water present. Sulfuric acid. We know that's an acid, so we're going to check our acid chart. Again, it's above the hydronium ion, so this is called a strong acid. So I can just copy this off my chart. H2SO4, aqueous, like all acids. Because it's a strong acid, it will ionize into its ions. So hydrogen ions and sulfate ions, and of course, water. Tetraphosphorus decaoxide. Well, both phosphorus and oxygen are nonmetals, plus they're using prefixes, so this would be molecular. This is not one of my memorized molecular compounds, so I just write it as is. So tetraphosphorus would be P4, decaoxide O10. I don't care what you decide to write here for a state out of solid, liquid, or gas. As long as it's not aqueous, it's solid, liquid, or gas for a molecular compound. Whatever state you put here, it would have the same state when you drop it into a bucket of water, because this is not one of our special cases. So I would leave it as a solid, and of course, water is present. If you decided back here this was a liquid, then this would also stay as a liquid. Ammonium hydroxide. It ends with hydroxide, cation, anion. This would be a base. So when I go to write this, it's going to be NH4OH. I check my solubility table. It falls under the very soluble, so it's going to be aqueous. When I drop this into a bucket of water, because it's highly soluble, it will dissociate into ions. NH4 positive, aqueous, OH minus, aqueous, and of course, H2O liquid. Chlorine. Well, chlorine we know is an element on the periodic table. Chlorine, I also hope you realize, is diatomic. So Cl2 gas. Because chlorine falls under the Me category, that means it's going to stay together. It's going to stay a gas. And of course, water is going to be present. The Me ones are easy. They stay together. We just have to think about the shag me part on whether they're going to change states. Elements don't do that. Propanoic acid. We check our chart. This would be a weak acid. Again, when I look up how to write propanoic acid, this is C2H5COOH. This is below my hydronium ion line, below my gray line on the acid chart. Therefore, it's going to stay together because it's a weak acid. C2H5COOH, aqueous, and of course, water is present. Now, we have one left, copper bromide. If you've done well up until this point, odds are you figured out that this one is also ionic because copper is a metal, bromine's a non-metal. The problem in this one was I got a little tricky. Copper has more than one possible charge. Since I didn't tell you what possible charge this was, we have to look it up, and it's the most common. This is actually copper 2 bromide. Therefore, when I go to write this, I'm going to write it as CuBr2. I'm going to look this up in my solubility table. And if I take a look, copper 1 bromide is slightly soluble. Copper 2 bromide is very soluble. So this is going to be aqueous. Therefore, when I drop it into a bucket of water, it will dissociate because it is highly soluble. Copper 1, low solubility. This is actually copper 2. So this is going to break into copper 2 ions, bromine ions, and of course, water. I hope these extra 8 examples made it easy to understand. Please, this is such a key concept. This is not only needed in Chemistry 20, but this carries through to Chemistry 30 and college and university. This idea of how do you know what's in the water when something dissolves in a solution is critical for many, many more aspects of chemistry.